Picking up on question number 22, we're kind of changing gears here. 22 and 23 go back to earlier in the semester when we discussed a flame test and what's going on there. One of the things we see in a flame test is we put different chemicals in a fire, we see different colors. Kind of our explanation for that is typically the metal that's in the solution or that we have on there is going to react to the flame, and the electrons that are in those atoms react to receiving energy. Let's remember that typically electrons, if we just want to draw them simply, are moving around the nucleus in specific orbitals, and they kind of hang out where they are. When we stick them into the flame test, the basic explanation here is that the electrons end up becoming excited, all right? And that's actually kind of what number 23's first, kind of misspelled things here. Excited, not exited, so excited. They get into this excited state because they gain energy. And so when they gain energy, they actually jump out to the next orbital, which isn't really there at the moment, and start occupying a position and a path around the nucleus that it ordinarily would not. It doesn't stay there very long because, well, it required energy to get out there, and that's just kind of not its natural place. And what it wants to do is it wants to return back to its original location, which on number 23 is called the ground state. When this occurs, the energy that it gained is subsequently lost. And one of our laws of science is you can't gain or lose energy, but you can only transform it. So it gains energy because it took it from the fire. When it loses energy, that energy needs to go somewhere, and it typically is given off in the form of a photon, which we normally think of more as light. When we see different colors of light, we see different colors of light because they have different wavelengths. And so longer wavelengths tend to be red, whereas shorter wavelengths tend to be blue. And there's a relationship between the wavelength and the distance that's going on right here. Therefore, when we have different types of metals and different types of chemicals, electrons are going to jump differently if I had copper as if I had magnesium or sodium. And because they jump differently between different elements, they give off different wavelengths, and these different wavelengths appear into our eye as different colors of light. So one of the reasons for a flame test is we can identify unknown chemicals based upon what colors are given off in a flame test, because particular elements only give off particular colors. And as a practical matter, this is one of the ways that a number of elements on the periodic table were actually discovered, was through flame test, where scientists actually saw different colors that weren't kind of accounted for at that point, and allowed them to dig into it a little bit further to kind of figure out what was going on and to identify elements that had not been identified up to that point. Changing gears with number 24, what type of force is acting on these? So we got three choices here. We got hydrogen bonds, we got dipoles, and we got dispersion. First of all of these occur in covalent molecules. Covalent molecules is when we don't have metals. These are going to be our non-metals, and these are going to be when they're sharing their electrons. One of the things about sharing electrons is they typically don't always share equally if they're two different elements. That has to do with the electronegativities that was in the previous video. Elements have different electronegativities, which means they have different desires and hunger for pulling onto an electron. If you remember back to the last video, fluorine is the most electronegative of everything. So fluorine's always going to be wanting to pull the electrons closer, even if it's sharing. It's not a perfect sharing. It's an unequal sharing that we have going on here. So typically we have a dipole-dipole interaction when we don't have equal sharing. That's going to occur when something is polar. The idea of polar, again, is you think of the Earth, we've got a North Pole and a South Pole. Things move from one end to the other. And molecules end up the same way if there's an unequal sharing of the electrons. If there's an unequal sharing of the electron, whichever element tends to be the electron bully ends up having the electrons hang out with it a little bit more often, more frequently. So that side of the molecule might end up being, might end up being negative, where the other side might end up being positive. So when I ask a question like this, one of the first things we need to look at is, what kind of elements involved. In each of these, we've got, these are all nonmetals. In the example of this one, it's a metalloid, but we don't have any metals involved. And so the first thing we're going to ask is it a polar molecule or is it a nonpolar molecule? for my purposes, and the rule of thumb is if it's two different elements, we're going to think of it as being polar. Now, this isn't always the case. There are some actually more specific rules that you can actually have two different things, and I'll go over one in a minute. Two different nonmetals, and they're technically still not considered to be polar because one of them is not that much stronger than the other one, or the geometry of the molecule is such that it ends up not being polar. But in general, if it's two different elements, it's going to be one of these two. We're either going to have a hydrogen bond or a dipole. Now, specifically, if it's got hydrogen in it and it bonds to one of the very, very electronegative elements like N, O, or F, it's probably going to be a hydrogen bond. Otherwise, it's going to be a dipole. So the hydrogen bond has to have a hydrogen in it, and it's going to stick to nitrogen, oxygen, fluorine. Okay? If it's two different elements, two different nonmetals, and it's not this situation, then we can call it a dipole. And then the dispersion force acts when basically we have something that is nonpolar. It's going to be nonpolar when there's an equal sharing, and that's typically when we've got an equal pulling, and that's largely going to be with something like Cl2, because no one's really winning this tug of war. Chlorine's pulling equally against the other chlorine, and the electrons kind of stay where they need to go. So in terms of classifying these, 24A would probably just call this a regular dipole, even though it's got hydrogen in it. A hydrogen bond needs to be bonding to either nitrogen, oxygen, or fluorine, which are in the second period. And since none of them are there, we can call this a dipole. B, we got hydrogen is sticking to oxygen, so this is a hydrogen bond. C, we've got two chlorines sticking together, so there's not going to be any buildup of pluses or minuses anywhere. So this is not very sticky at all. And this will be a dispersion force because it's a nonpolar molecule. And then this last one, D down here, when we've got phosphorus and chlorine. Again, I've got two different nonmetals. Chlorine is much more electronegative than phosphorus. And so we're going to have a polar molecule, right? And since it's a polar molecule, it doesn't have hydrogen in it. So we could be a little bit more specific and call this a dipole-dipole interaction with that one. So a lot of that you may just have to make some note cards for just to remember what the facts are on this. 25 through 28, we are just kind of talking about the type of compound, whether it's ionic or covalent, and give it a name. So remember, if it's two nonmetals, it's going to be covalent. So we can usually look at the very first term to figure that out if it's going to be, if it's a positively charged thing. So sulfur being a nonmetal, this is going to be a covalent, right? The second one on 26, nitrogen, also is going to be covalent. 27, I've got sodium, which is a metal, so it's going to be ionic. And 28, again, nonmetal with phosphorus, this is going to be covalent. Covalents are the ones we use our prefixes for, and so we need to remember our prefixes. We've got mono, we've got di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. And remember, we don't use the prefix for mono in the beginning. So number 25, we put these together. I've got one sulfur, so that would just be sulfur. And I've got 6 chlorines, so I need to use the prefix for 6, which is hexa. And then I need to take chlorine and change it into the IDE version of chlorine, which is chloride. 26 was also covalent, so we need prefixes. Again, no mono at the beginning, so it's just nitrogen. And then 3 bromines is tri-bro, IDE ending, ide. 28 would also have prefixes because it's covalent. I've got 2 phosphorus, so I have diphosphorus. And I've got 5 oxygens, and I need my prefix for 5, which is penta. And don't put the A and the O together because it just doesn't sound right. So instead of pentaoxide, it's just pentoxide. So diphosphorus pentoxide. 27 is ionic, so the rules for naming ionic, so we just need to write down what we've got here. So I've got Na is sodium. And then PO4, this is where we need to go back and we look at the back of our periodic table and we make sure that we're not writing PO3 or PO any, make sure we're getting the right one on here. So don't rely on your memory. PO4, if you go and check it out, is phosphate, not phosphide. So we write sodium phosphate on this one, Na3PO4. If we do the reverse on the ones beneath that, if we do some formulas, again, we don't think is it ionic or is it covalent? Covalent ones are pretty easy because those are the ones that have the prefixes to them. So I can just kind of start over here. So carbon tetrachloride would be 1 carbon, tetra is 4, chloride is chlorine. Dinitrogen is 2 nitrogens. Dioxide is 2 oxygens. Over here, a little bit more complicated because we need to take our charges into account. So calcium, I need to go figure out which column it is on the periodic table. It's in the column that has the +2 charge. Chlorine is a -1. Our rule here is to write our symbols, crisscross our numbers. It gives us calcium chloride, CaCl2. And then copper 2 sulfate. Copper is a transition metal, so it's got a Roman numeral. That Roman numeral tells us the oxidation number, the charge, which is +2. So I would write copper. And then again, I need to find sulfate, which is not, it's not just an S. I need to look up sulfate on the back over here. So just double checking. Always good to double check. Sulfate is SO4. Sulfate also has a charge of -2, which I can see on the periodic table on the back on the chart that we have there. If I've got +2 and -2, then when I crisscross, I get a 2 and a 2, which I can reduce. And so I don't need to put any numbers down here. I also don't need to put a parentheses around the SO4 because there's only one of them. And that would be my formula for copper 2 sulfate.